Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In today's hyperconnected world, reliable access to the internet no longer depends solely on Wi-Fi or wired networks. Cellular technologies have become an essential part of both personal and enterprise connectivity strategies. From mobile phones to industrial IoT sensors, cellular provides wide-area, mobile-friendly access that works independently of local infrastructure. It fills in the gaps when Wi-Fi is unavailable, unreliable, or unsuitable, offering an alternative path to the cloud and the web from virtually anywhere. This episode explores the role of cellular in modern networking. We'll break down how it differs from Wi-Fi, examine key cellular standards from 3G to 5G, and explain how frequency bands and SIM-based authentication work. Whether you're managing mobile devices, troubleshooting WAN failover systems, or studying for the Network Plus exam, understanding cellular is essential to a well-rounded view of network connectivity. At the heart of cellular networking is the concept of geographic segmentation. The network is divided into cells, each served by a base station or tower that handles radio communication within that zone. As a device moves, it hands off its connection from one cell to the next, enabling seamless coverage over large areas. These networks are managed by cellular providers and are designed to support both voice and data traffic. Cellular technology allows users to remain connected while traveling without relying on local Wi-Fi or physical cabling. The third generation of cellular technology, commonly referred to as 3G, introduced meaningful mobile data capabilities. While earlier generations focused primarily on voice, 3G enabled internet access, streaming video, and mobile email. Standards like UMTS, Universal Mobile Telecommunications System, and HSPA, High-Speed Packet Access, offered significant performance improvements, supporting speeds sufficient for web browsing and basic app functionality. 3G was a foundational step toward the fully IP-based networks of the future. Fourth-generation technology, including LTE long-term evolution, took mobile networking to a new level. 4G represents a full transition to an all-IP network model, meaning voice and data are treated as packetized traffic rather than using separate systems. LTE offered much faster speeds, lower latency, and better support for multimedia. Most modern smartphones rely on 4G or LTE networks today, and even when 5G is available, many devices fall back to LTE in areas where the new infrastructure isn't yet deployed. The next leap forward is 5G. This fifth-generation standard brings dramatically increased data rates, ultra-low latency, and the ability to support far more devices per square mile. 5G networks are designed to support dense environments, like stadiums, cities, and factories, while enabling high-speed video streaming, real-time gaming, and augmented reality. 5G also supports new deployment models like network slicing, where dedicated virtual networks can run on the same physical infrastructure, tailored for different use cases, such as emergency services or autonomous vehicles. Cellular communication depends heavily on the radio spectrum, and different bands affect performance characteristics. Low-band frequencies, below 1 GHz, offer excellent range and wall penetration but lower speeds. Mid-band frequencies offer a balance of range and bandwidth, while high-band, also known as millimeter wave or wave, delivers extreme speeds over short distances but struggles with obstacles and interference. Each provider uses a mix of these bands, and performance depends on what's deployed in a given area. Understanding spectrum usage helps technicians set realistic expectations about speed and coverage. At the core of every mobile connection is the SIM card subscriber identity module. This small chip stores the subscriber's identity, encryption keys, and network authorization data. When inserted into a compatible device, the SIM card tells the carrier who the user is and what services they are entitled to access. This enables the device to connect to the provider's infrastructure and gain access to voice, text, and mobile data services. SIM cards can be physical or embedded eSIM, and they're essential for authentication and mobility. In enterprise or advanced networking environments, access point names, or APNs, define how cellular data is routed. The APN configuration on a device determines the gateway used to access the internet or a private network. Businesses with mobile workforces or remote equipment may use custom APNs to direct traffic through their own secure gateways or VPNs. Without a valid APN, even a device with good signal strength and an active SIM won't be able to transmit data. Speaking of sharing data, mobile hotspots and tethering allow one device to act as a gateway for others. A smartphone can share its cellular connection via Wi-Fi, Bluetooth, or USB, turning it into a temporary router. Dedicated mobile hotspot devices serve the same purpose, but often support more connections and better battery life. These tools are invaluable for remote work, travel, or backup internet when Wi-Fi is unavailable. Administrators may also deploy mobile routers in branch offices, vehicles, or temporary sites using cellular for the WAN uplink. The distinction between cellular and Wi-Fi is fundamental to network design. Wi-Fi uses unlicensed spectrum, is locally managed, and supports high-speed communication within a limited area. Cellular uses licensed frequencies, is managed by carriers, and supports broader coverage across wide geographies. Wi-Fi is often faster in local environments, but it depends on localized infrastructure. Cellular offers less customization, but is generally more resilient to local disruptions and doesn't rely on an organization's internal network. Knowing when to use each technology or how to use them together is a valuable skill. For more cyber content and books, please check out cyber.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. One of the fastest growing applications of cellular connectivity is in the world of IoT, Internet of Things. Devices like smart meters, remote sensors, security systems, and connected vehicles increasingly rely on cellular for communication. These systems often use embedded SIMs, eSIMs, which are built directly into the hardware and provisioned remotely. The benefit is always-on connectivity without relying on Wi-Fi or wired infrastructure. In remote, mobile, or outdoor locations where traditional networking is impractical, cellular provides consistent and scalable access to the internet or centralized platforms. Private LTE and private 5G networks are emerging solutions that allow enterprises to deploy their own cellular infrastructure. These are not dependent on public carriers, but use licensed or shared spectrum and carrier-grade base stations within a confined space. Factories, warehouses, and campuses use private cellular to support automation, robotics, and safety systems. These deployments allow for strong coverage, low latency, and predictable performance without relying on Wi-Fi or external service providers. Managing a private LTE or 5G network requires planning and equipment, but it brings carrier-level mobility and reliability to local network environments. Cellular failover is another critical use case, especially for business continuity and resilience. Many routers and firewalls now include SIM slots or USB ports to connect to 4G or 5G networks. When the primary wired connection fails, the router automatically switches to cellular as a backup WAN uplink. This ensures that services remain available even during ISP outages or fiber cuts. Failover configurations must be tested regularly, and data usage should be monitored to avoid overages during extended outages. Cellular backup is now standard in retail, healthcare, and remote branch deployments. Coverage varies dramatically based on geography, provider, and physical surroundings. Urban areas generally have dense coverage with overlapping towers providing strong signals and fast data rates. Rural areas may have limited tower presence, resulting in slower connections or even complete dead zones. Signal strength is also affected by terrain, building materials, and weather conditions. A remote location surrounded by hills or trees may receive poor signal despite being within coverage maps. When deploying cellular systems, always test performance on site, using multiple carriers and bands if possible. Data usage and billing are ongoing considerations in cellular networking. Most cellular plans have data caps, throttling thresholds, or overage charges. For IoT deployments and mobile routers, real-time usage tracking is crucial. Many enterprise solutions include dashboards that show current and historical data consumption, alert thresholds, and line status. This helps avoid bill shock and ensures that cellular connectivity remains available when needed. Even in personal hotspot scenarios, knowing how much data has been consumed helps users manage performance and cost. Roaming and carrier switching play a key role in ensuring global and cross-regional connectivity. Roaming allows a device to connect to partner networks when outside its home carrier's coverage area. This is seamless in most cases, but roaming may introduce latency, incur extra charges, or have reduced speeds depending on the agreement. Advanced devices may allow manual network selection, useful when a preferred carrier is underperforming. In international scenarios, selecting the correct APN, understanding data plans, and validating frequency compatibility are all essential for reliable connectivity abroad. On the Network Plus exam, cellular topics are tested primarily through recognition and comparison. You might be asked to match features to 3G, 4G, or 5G standards. For example, 3G may be associated with YUM and Electrican integration, 4G with all IP and LTE, and 5G with ultra-low latency and dense IoT support. You may be asked to identify the role of a SIM card, recognize the function of an APN, or explain why a device fails to connect over cellular while Wi-Fi works fine. You may also encounter questions that ask you to distinguish between licensed, cellular, and unlicensed Wi-Fi spectrum use. To summarize, cellular technology expands network connectivity beyond the limitations of Wi-Fi. It allows mobile, remote, and embedded devices to communicate without fixed infrastructure. The progression from 3G to 4G and now 5G brings greater speed, lower latency, and support for more use cases. Frequency bands determine coverage and performance, while SIMs and APNs control identity and routing. Whether it's for user mobility, IoT integration, WAN failover, or private enterprise deployments, cellular has become a core pillar of modern networking. Technicians must understand how to configure and troubleshoot cellular devices, interpret signal behavior, and work with carriers to provision service. They must also be able to compare wireless technologies and explain when to use each one. In the exam environment, this means confidently identifying generations, explaining the function of mobile network components, and recognizing where cellular fits into the broader picture of infrastructure and support. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.